Frequency Electronics has built precision timing and frequency control systems for 65 years. We've spent decades learning how to deliver accurate, stable, and reliable timing systems and components. When I joined FEI in 1984, our focus was on quartz and early atomic clocks. Today, we're building advanced atomic clocks and quantum sensors with our team of world-class physicists and engineers.
Before joining FEI, I spent 5 years at NIST and 13 years in total developing atomic fountain primary frequency standards. This involved performing accurate microwave spectroscopy to measure the quantum state of laser-cooled cesium atoms. We achieve incredible performance with the fountains, corresponding to losing less than 1 second over 100 million years. The NIST F4 primary frequency standard calibrates the rate of the official US time called UTC NIST.
FEI leverages the same principles of quantum mechanics outside the lab. Our mission is to transform lab-grade R&D into real-world solutions. We're currently working with mercury ions, nitrogen vacancies, and diamond and Rydberg atoms. Our engineers build products for practical size, weight, and power specs. We test them for large temperature, vibration, and EMI, EMC environments. Then we optimize the whole system to deliver the highest performance in the harshest environments.
Because of its reliability, quartz has been the foundation of precision timing for nearly 100 years. Modern atomic clocks still rely on quartz to generate the signal and atoms to discipline the oscillator. The better the quartz, the better the clock. With decades of flight heritage on mission-critical space programs, FEI quartz oscillators are trusted for uncompromising accuracy.
We don't just buy finished crystals and assemble the parts. We control the entire manufacturing process. We buy the best quartz in the world, then use a diamond wire saw to cut the crystals with the precision of thousandths of a degree. The crystals are then mechanically processed and mounted for assembly into resonators, which are installed into oscillators. Each oscillator is tested for temperature, shock, and vibration, and then fine-tuned for performance. We've also manufactured rubidium atomic clocks in-house for decades. Our glass blowers use torches to form and seal dozens of vapor cells. We fill each cell with a mix of rubidium atoms and then buffer gases. And then the microwaves provide the atomic transitions to keep the oscillator on frequency in a feedback loop. Each of our units are tested until every clock meets strict specifications before they leave the building.
Our timing unit rubidium oscillators are smaller than our vapor cell clocks used for space and defense. Turbo is a compact, rugged unit built with digital controls that enable us to deliver atomic stabilized timing for mobile and autonomous systems. Turbo continuously compares its internal oscillator to rubidium atoms to maintain long-term accuracy and stability. Its all digital control and compensation logic corrects for temperature, vibration, and other environmental effects.
PopRefs uses the same digital controls to push the atomic physics further in stable environments. Instead of continuous excitation of the atoms, we used pulsed lasers and microwaves to precisely control when the atoms are prepared, interrogated, and measured. Separating these steps allows us to reduce atomic noise, which improves long-term stability and holdover for space and fixed timing systems.
Mercury ion clocks are fundamentally different from vapor cell clocks. They push you into another level of physics. Unlike our rubidium clocks, a cloud of mercury ions is trapped by electromagnetic fields inside an ultra-high vacuum chamber. The trap isolates the ions from collisions and disturbances. This eliminates drift, improving long-term stability and holdover.
NV diamond magnetometers take a different approach. Instead of atoms in a vapor cell, the diamond is a solid-state sensor. Nitrogen vacancy centers embedded in the crystal lattice allow us to measure Earth's magnetic fields on multiple axes to capture the full vector direction. Green lasers prepare the quantum states while microwaves probe them. When a magnetic field is present, we measure these energies in the diamond's red fluorescence. Diamond's rigidity keeps the response stable over time, which enables aircraft or autonomous systems to stay on course during GPS outages.
Rydberg sensors respond to RF fields at the atomic level. As lasers excite alkali atoms into a high energy state, it dramatically increases the atom's size and polarizability. This makes the atoms uniquely sensitive to electric fields and consequently to electromagnetic radiation from DC to terahertz. This allows compact vapor cells to act as receivers, enabling wideband sensing and optical frequency tuning on much smaller platforms.
From quartz to quantum, FEI continues to push the boundaries of physics and engineering. Our atomic clocks and quantum sensors are built on decades of institutional knowledge that compounds over time. A lot of companies don't last in this space. Frequency electronics has been around for 65 years because we respect the physics and we take the time to get it right.